the main collector for Marsh, was John Bell Hatcher. He encountered a specimen that came from this particular location in late 1887. And so he came to this location, to the rancher. The rancher took him out to the locality, showed him the original specimen, which was a Triceratops skull, and then came back for four consecutive seasons digging dinosaurs out of this locality. First of all, the first specimen shown here, let's see if I can get used to this thing. Shown here is the holotype for Triceratops. Yeah, I'm going to mess up here. The Triceratops horridus. That is the type species that's the type specimen for that species. It is thought by most people to be the only species of that particular genus, even though Marsh described 15 species of this from this genus. It's also from this same locality that if you go to the Smithsonian and see the exhibit of the Triceratops, the mount, both the skull and most of the bones of the body were taken from this locality by John Bell Hatcher. They're not from the same specimen, but from multiple specimens. The skull at the American Museum, the mount, the rest of the skeleton is actually from a different state, but the skull is from this locality, collected by Charles Sternberg some 20 years after John Bell Hatcher's work. Also found by John Bell Hatcher at that time was the holotype for the genus Torosaurus, which some people would like to just fold into Triceratops. So it's another one of the ceratopsian dinosaurs. Also, the holotype for Thescelosaurus neglectus is also found in this locality. The holotype for Edmontosaurus. Holotype means the specimen that was used by the scientists to describe that particular species. It's not necessarily the first specimen. Hopefully it's the best specimen, but it's usually a compromise between those two, either the first or the best specimen that's used to describe the species. So the big duck-billed dinosaur Edmontosaurus was first discovered in this locality. It is a very large dinosaur. Standing upright, he wouldn't fit in this room. He's taller than that. His femur is about 5 feet long, so the upper leg bone here is 5 feet, so he's a big guy. And if you're familiar with Art Chadwick's dig, which is to the north of this locality about 20 miles, this is that is a dig site into a bone bed that's almost exclusively Edmontosaurus. Also in this locality are the only mummified dinosaurs known in the world. Charles Sternberg and his sons collected 2 specimens in the earliest part of the 20th century. One specimen is in the American Museum of Natural History, and the other specimen is in Frankfurt, Germany. Subsequently, just less than 10 years ago, 2 more mummies were found, again from this locality, the only place that mummified dinosaurs have been found. This is also the type locality, the locality where the type specimen for Pachycephalosaur, the main one, the one people most know about, Pachycephalosaurus wyomingensis. The original specimen only looked like this. A beautiful recent specimen was found only about 20 years ago by one of the ranchers up in that same locality. It's also near this location, actually up about right here, that the first Triceratops, no, not Triceratops, Tyrannosaurus rex, there we go. T-Rex, first T-Rex was found in this locality as well. So this is a very important locality. John Bell Hatcher, in his 4 years, found 32 Triceratops specimens and hauled them out of here and sent them by rail to Yale University, where Othniel Marsh was. They're represented by all these triangles throughout this region. He found 6 Edmontosaurus specimens, also sent to Yale, and he found thousands. Estimates are somewhere around 5,000 mammal fossils in the same deposits. Tiny, tiny little things, almost microscopic, and 13 different localities indicated by whatever that color is, purple. So just that one collector collected an awful lot of material, and it's the Lancian mammals. That's a particular age of mammals, is named after the mammals that come from this locality. So this is a very important locality historically. If you look at all of those localities, and you look at the rock that they're found in, the rock is exposed in this region indicated by this strange orange color. Originally, that rock was known as the Ceratops beds because the Triceratops was found in it, but it breaks the rules of geology to name a rock after a fossil. Not supposed to do that. If you're going to name your rocks, you got to name them after a locality. So it was changed to the Converse beds because it was originally found in Converse County. However, in 1910 or 11, somewhere around there, Converse County split and created, in the eastern portion of it became Niobrara County. So this wouldn't do. So they changed the name to the Lance Formation. The Lance Formation is named after the creek, Lance Creek, that runs through this locality here, and it's right in the middle of all of these specimens. So again, a geological rock formation is supposed to be named after a geographical site, and it's best not to name it after counties that change their names and all that sort of thing. So ultimately, it became known as the Lance Formation. The Lance Formation in the pile of rocks that we have in the geologic column is up towards the top. It is in the top of what's called the Cretaceous set of rocks. It's the very topmost Cretaceous formation. And it's a total of, in the type locality, which is the locality where it was first discovered, it's almost a half mile thick. So it's a very big formation, very big rock unit. The rock unit is made of 3 different types of rock. Most of the unit is made of mud, so what we call a mudstone. You can also call it a shale. The second most abundant lithology or rock type in it is sandstone, and then there are some lignite stringers. In other words, little itsy-bitsy little coal seams that are less than an inch thick and usually can't be traced very far. John Bell Hatcher, with this information, 2,500 feet of this kind of rock, and the fact that dinosaurs were found in it, concluded that the rock was created by braided streams. So the idea is that creeks that are on a very flat plain separate into meandering, if you wish, tributaries moving downstream. You've got sandbars scattered throughout. When the spring rains come, it overflows its banks and dumps a bunch of mud on the outside and over the sandbars. And so over long periods of time, so the story goes, the braided streams deposited a total of a half a mile of mud and sand, and then the lignite stringers would be from the trees that were found alongside of it. Okay, so that's the traditional interpretation of how we're to understand this particular unit. John Bell Hatcher introduced the idea, and it's been believed ever since. It's also, by the way, the very top of this formation is an iridium anomaly that has been pointed to as evidence of the asteroid impact that killed the dinosaurs, because this is the very last formation that has any dinosaurs in it. We have dinosaurs all the way up to the top of the formation, but the formation above it, the Fort Union, has absolutely no dinosaurs. And nowhere else on the Earth does anything above the Cretaceous have dinosaurs. So it's, again, the conventional wisdom is that asteroid impact killed them all. It's interesting that even though the Lance Formation has been known and studied for over a century, it's actually not been well studied, partly because of John Bell Hatcher's claim that it was a bunch of braided streams. If it really is created by a bunch of braided streams, then the sandstone units are just lenses. They don't, they're just sandbars, so you can't follow them very far. So there's no layering in this deposit that would tell you where you're at in the deposit. The bottom of it would look just like the top of it and look like the middle of it. And so everybody has thought, well, it's no use if it's in the Lance Formation. We don't know whether it's the top, the bottom, the middle, wherever it's at. We just call it the Lance Formation. So most people have been scared to death to do any research in it because people think that you can't find your way through it. Another problem with it is that there is no type section. In geology, when we officially name a rock unit, we have to declare a location, which is called a type section. That's the place where that particular rock outcrops very beautifully, where people can see it, and it's well evidenced with everything that you would expect in that formation. And it gets the official name for that particular rock, and it's actually the only rock that has that name. Every other place gets that name only by similarity to that type section. So technically, only one location has the name Redwall Limestone, for example. That's one of the units in the Grand Canyon, named after a red wall of limestone that John Wesley Powell saw when he came around the curve in a river. That is the type locality. That's the type section right there. The only place that literally has the name Redwall is at that particular location on the Colorado River. All other places that are called Redwall are only Redwall by similarity to that one. Okay. In this particular case, there is no type section. This breaks, again, more of those rules of geology. Because there is no place where this half mile of sediment is found in one pile, and because nobody thinks they can tell what's the top and the bottom and the middle and that sort of thing, a type section has never been declared. John Bell Hood didn't do it, and no one's done it since then. A couple of sort of tried. Back in the 1950s, Clemson tried, but he wasn't successful. And so there's no type section, so instead we have a type area. That whole area that John Bell Hatcher found the specimens in, which is in excess of 100 square miles. It's 120 square miles of area is the type area. Now that makes studying this formation really tough because there's no one place to look for what the formation's supposed to look like. Basically, if you're going to do a good job, you've got to cover 120 square miles of area to do it. So I endeavored to tackle this problem, to in fact determine what the stratigraphy of the formation is. Are there in fact layers that can be found across the entire unit? Can we divide the unit up? Can we get a type section for the unit? Can we figure out where we are in it? Why do I want to know that? Well, up here, about 15 miles to the north of the Cheyenne River here, is Art Chadwick's dinosaur locality, and it's in this formation. It's in the Lance Formation. But again, we don't know where it is in the formation. We don't know. We suspect it's somewhere near the top of the formation, but we don't know where it is, and we'd like to know where it is. And since I'm on the board of the Hansen Research Station, for many years I've wanted to know if we're going to study this formation so well up here, we've got to know where it is in the type locality. And so my job then, I set about 4 years ago to figure out what the stratigraphy is so that eventually I can make my way up to that location and figure out where that dinosaur site is. What I've found in going over that area, I've only covered about 80 square miles of the 120 square miles at this point in time. I'm about wore out, and none of my field assistants will come back and help me the next year. They all get worn out. So some of the things that I've found, I'm reporting on. This is all part of the Lance project, trying to figure out the structure of the Lance. First of all, we have shell beds. There are certain layers that have lots of shells. This looks like lots of shells. Yeah, and you follow these crazy things for a half mile in all directions. That's a huge number of shells. This is not what you find in braided streams. You just don't find shell beds spread over half a mile in all directions in braided stream situations. So something's not quite right with the braided stream interpretation. Plus, a number of these shells are actually closed, and you know that a pelecypod clam shell, when it dies, it releases the hold on the shells, and the shells open up. So when we find closed shells, especially when we find most of the specimens being closed, it means that the little clams were alive at the time they were buried. These clearly didn't live here. They wouldn't live in this high a concentration. They were carried here, but they were carried here while they were still alive. So they were disinterred from wherever they were living, carried to this location, and spread over a huge area by some process. Second observation, we've got bone beds. One of the beds, the most famous at this point, would be the bed that Art Chadwick has been digging dinosaur bones out of. Since 1996, when we first went out there and set things up there, he's been going out every year and collecting about 1,000 dinosaur bones out of one bone bed, out of one layer that is less than 3 feet thick. He's been taking out 1,000 bones every year, and you can barely see that he's made a scratch on what's there. We figure you can do that for 500-600 years and still not even get off the ranch that it's found on. There's at least 5,000 acres of this bone bed. Many tens of thousands of specimens of Edmontosaurus, basically one species of dinosaur. So that's one bone bed. It's not the only one. There are several bone beds in the unit. That one has been studied the most. What's interesting about this bone bed, and this is a picture not from his locality, it's one from about 2 miles away, something like that. A ranch owner was having someone dig out some Triceratops bones so that he could sell them. And I got a chance to take photographs of the site before they ripped everything out and sold it. And this was interesting to me because the formation, you can see the layers of mudstone, of shale here. See that here. The dinosaur bones, here's one here, here's one here, here's one here. The dinosaur bones are not in the layering of the formation. In fact, this one is perpendicular to the layering. It's really interesting when I talk to the excavator, who's, again, he's just in the business to sell bones. He digs them up, sells them, gives a certain percentage to the landowner, and keeps the rest for himself. I asked him, well, what do you think about all this? And he gives me the standard story, the braided stream and all of that. I said, well, what about this bone? It's vertical. He says, I don't know about that. I don't understand that. What he's going to do is he's going to take that bone out and he's going to put it with the other bones. He's going to lose the information on its orientation, and it's all lost. And that's the problem. That's what I don't like about people who dig out dinosaur bones and fossils in general. They don't care beans about the situation. I sort of see myself as a forensic paleontologist, someone who's going in to figure out what happened here. How did this critter die? Well, if it was a human body, you wouldn't be allowed to just take the bones out without noting their orientation. That might tell you something about how they died. Might give you important information. In fact, by the time you see it put together in a museum from multiple specimens, you've lost all the important information. You actually don't know anything about that. And everything that's of interest to me has been destroyed. And here, You've got it right there. It's vertical. How do you explain that? I said, you can't explain that. I said, here, I asked you a question, too. You've been digging in here. You took bulldozer. I saw the bulldozer sitting right there. He bulldozed the stuff off the top, and then he is working through and getting all the bones, and he's going to bulldoze ultimately all that out. And I said, did you perchance dig through 2 feet of shale, of mudstone, that you didn't find any fossils in? Yeah. How did you know? I said, on top of that, there was a sandstone, wasn't there? Yeah, there was sand rock on top. They call it sand rock. There was sand rock on top of it. Yes. Okay. And is there any place that you actually dug underneath here to see if anything's underneath? He said, yes. I said, wait a minute, before you say it. You found 2 feet of mudstone underneath with no fossils in it, with sandstone underneath that. He says, yeah, how did you know? I said, well, I've seen this a lot of times. I see a unit that's got our bones in it. Let's say it's 6 feet thick. Top 2 feet, no bones at all. Bottom 2 feet, no bones at all. All the bones are in the middle. And the bones that are in the middle, they vary from being horizontal to angled to vertical. What in the world's going on there? Well, if you know anything about Steve Austin's nautiloid bed in the Grand Canyon, we have an explanation for this formation. When you have an underwater landslide, an underwater mud flow, which is basically a bunch of mud moving as a unit underwater, let's say it wasn't underwater, let's say it was above, it was in the air that it was doing this. The bottom of the mud flow is in friction with the ground. So it's moving slower than the middle of the mud flow. The middle and the top of the mud flow are moving at a certain speed, but it's getting slowed down below that, so that if there's anything in that lower part, it gets turned and actually rotates if the thing goes far enough. And Steve's nautiloid bed goes for over 200 miles. Okay, so if it goes far enough, it'll rotate these things into the middle, and they'll be in various orientations there. Some will be flat, some will be at an angle, some will be vertical. Now, that will be if you're in the air. But if you're underwater, a significant amount of water, so that there's water bearing down on the top of it, then the top will also not be moving. And so the top portion of it will also rotate bones or anything large, anything long, will rotate into the middle. So if you're under significant depth of water, you will rotate all your big, long things into the middle zone, and they'll be at various cockeyed orientations. This is an underwater avalanche, underwater mud flow that has gone for a very long distance, probably at least tens of miles, and it's got to be under more than 100, 200 feet of water. Okay? That's not a braided stream. Okay? There is no way this can be a braided stream. So here we have evidence of an underwater mud flow that cannot be explained by the braided stream idea. Another observation, we have cross beds. We have the normal bedding of the sandstone, and then we find bedding that goes at an angle to it in a particular bed. There's angled bedding within that bed, and that's called cross bedding in that sandstone. That's indicative of the sandstone being generated by, the sand is being brought in by a current of water or air or something of that nature. So you have imagine a sand dune. Wind might carry the sand up one side of the sand dune and cascade the sand down the other side of the sand dune. So as the sand dune moves across the surface, it produces these cross beds as it does so. Water does the same thing. Water can pick up sand, carry it over the top of a dune, cascade it down the front, and produce these. In this case, the water is moving, or wind is moving this way. It's cascading down the front side and moving across the landscape. The next dune comes along and cuts the previous dune off about halfway up. So you have these things cut off at pretty high angle. They would have gone up this same height again to the top of the dune, but the next dune comes along and cuts them off. So these crossbeds indicate that we had some sort of medium water or air is moving sand. And we have crossbeds in excess of 3 feet. That means that the original bed forms, the original dunes, were in excess of 6 feet in height. That's a pretty big dune. You need 5 times the height of a depth of water to produce that depth of a sand dune. So a sand dune that's 6 feet high requires at least 30 feet of water. That's a lot of water, unlikely in a braided stream. Okay, you can get 30 feet of water in a narrow passage in a canyon, but braided streams are on very large plains. That's the only way you can get that braided stream. You can't get 30 feet of water in a braided stream unless you're near the coast and got the hurricane comes in and with the water in front of it. But there's no other way to do this. This is not a braided stream. Plus, we have crossbeds in conglomerate. This is conglomerate. The particle size here is not sand. Sand is qualified as sand up to about 1/8 of an inch in diameter. The little particles, 1/8 of an inch in diameter. Anything above that is called a conglomerate. And air can't blow sand particles that big. It can't move them. So you can't produce these crossbeds in the air. You can only produce them underwater. So we have, these things are evidence of underwater deposition with at least 30 feet of water and moving at a very good clip. Let's see. In this particular case, we've got to have a velocity of water that's in excess of 1 meter per second. That's moving very fast. And again, it's 30 feet, at least 30 feet deep over its entire breadth. That's, again, not a braided stream. It's not a situation we're familiar with in the present at all, anywhere on this earth, even in the midst of a hurricane. Another issue. Even though braided streams, Bell Hood's original claim was that these sandstone units can't be traced very far because they're just, there's these sandbars. Nonetheless, here's a picture I put together from several photos because it's too wide to see another way. Here's a sandstone unit that looks like it can be traced in excess of a half a mile. It's a beautiful particular exposure. By the way, this is really fun because this road's on a map from 1897. This is the only road that was in that area at that time. Geologists have been traveling this road for over 100 years. Right through this, the road goes right through and up, cuts right through this unit. So they've been seeing this unit for over 100 years. Now this is a sandbar that's in excess of a half mile maybe it's the length. Maybe we just got, long the length. We're going to see if that's, but there's a clue that maybe they are continuous. Maybe they are not discontinuous. Here's a picture from that. I'm over here taking a picture looking this way. And there's the unit. I mean, it's as flat and as uniform as can be for as far as you can see in this particular. It's kind of unusual around here. You can see what you usually have, grass. That's the other challenge in this area. It's hard to find places to find the rock, and you have to piece things together generally. So that got me to the actual project. The first year, back in 2015, I mapped this particular area, which is 6 square miles of area. Here's the topo lines, the major topo lines. We're at nearly a mile. Lance Creek is over here. It's between Buck Creek and Lance Creek. Buck Creek comes into Lance Creek up to the north. The boundary between the Fox Hills Formation, which is the unit just below the Lance Formation, and the Lance Formation is found here. So I concentrated my effort there in the bottom of the Lance Formation. Here are all the gullies. It's grass everywhere else. You just have to basically follow the gullies and hope you can find rocks and put all the pieces together from And here are 5 of my sections along 6 miles total length. And sandstone is represented by the yellow and shale by the white. And I've got sandstone units that I can trace across all 6 miles. So these are not just a half mile like I can see visually, but there's good reason to believe that these sandstone units can be traced for at least 6 miles in an east-west direction. Now, just in case it happens to be along the length of the creek, okay, just got lucky here. My next year's project was to map the 60 square miles to the north of that. That was what I did in 2016. I do this in about 10 days, so I do about 6 square miles a day. There's a reason I limp now. Here is a topo lines plus these indicate where I actually found rocks and went down gullies, and I numbered the gullies for my own purposes. And putting all the pieces together, I have reason to believe I can follow this particular unit, which I called the 4300 unit because it's at 4,300 feet above sea level. That particular unit I can follow across all 10 miles north-south and 6 miles east-west. Last year, I worked on this side of the other side of the Lance Creek. There were some challenges there, and I haven't analyzed all my data yet, but it basically confirms what I found the previous year. What I've found is that you can trace these sandstone units 6 miles in an east-west direction and 10 miles in a north-south direction. So we've got sandstone units that are 60 square miles in area, and I've got a couple dozen of them. So these are not braided stream deposits, okay? There's just no way. These are sheet sandstones. They are found over vast areas, so we call them sheet sandstones. And we know of only one place that sheet sandstones can be produced, and that's underwater, specifically in the modern world, in the marine realm. Next, convoluted bedding. This was weird. I see sandstone, which has got this kind of bedding in it. That's weird. Okay, it's not cross bedding. It's beautiful. This particular one is beautifully curved. It's what in the literature for some time they called convoluted bedding. And this particular, the Lance Formation is well known for its convoluted bedding, even though that's never been published. Nobody's ever published it, and I think I know why, because no one can explain it. This is weird stuff. Okay, here is the explanation for convoluted bedding. Let's say when sandstone is originally deposited, when sand is originally deposited, especially underwater, it is not close packed. The sand grains have a bunch of water in between them, and they can be put into a more compact form, but they're not deposited that way. This would be like, you can do this in the air too. Fill your jar with marbles and then shake it. And then they go down, right? And you can put more marbles in it. Or put flour into something and shake it, and it goes down. You can put more flour in it. Same principle, okay? When you first deposit something rapidly, it does not close pack initially. But if something comes along and shakes it, it will close pack. In other words, the particles will get as close together as they can, and if there's water in there, it'll force the water out from between the sand grains. And the water will rise, getting to the surface, and if there's any layering in the rock above that, it turns the layering up. It twists the layering, produces something called a fluid evulsion structure. It's evulsing the water out, and any layering that was there is going to get convoluted in the process. We see this in the modern world after earthquakes or during earthquakes. During earthquakes, you can be in a field like this particular instance, Loma Prieta. We're in a field here. You can see the crops in rows. And all of a sudden, during the middle of the earthquake, water comes springing out of the ground in certain spots. water volcanoes. The water comes out, carries a bunch of sand and debris with it, and forms these volcanoes that they're not volcanoes and lava or anything like that. It's just mud and sand that's brought up because underneath, the material that was waterlogged has been packed down. The water comes out, fluid evulses out of these things and produces these volcanoes. Extreme examples of this, it can fluidize a sandstone. It can, from the stuff underneath, water can come up and put so much water into a sandstone that it becomes a quicksand. And cars can disappear into it. Or buildings can fall into it, okay? If you are stupid enough to build your building on sand, okay, didn't follow Christ's recommendations there, you built your building on sand, you have this kind of thing happening, okay? Californians haven't figured this out yet. Neither are people in Japan, even though earthquakes are very common there. Yes? No, and that's going to be part of the argument here. It can only be soft, it can only be sand, and it's got to be full of water. If it isn't full of water, nothing like this happens. Water doesn't come up and it doesn't fluidize and that sort of thing. And if it's hard, it won't close pack. So it's got to be before it's lithified, while it's still sand, and while it's still or subsequently full of water. Both of those things have to be. It's got to be soft and full of water for these features to be created. So if you're familiar with Steve Austin's work in Death Valley, he's been studying the sediments in the Dead Sea. The Dead Sea is great for geologists, bad for biologists. It's a dead sea. There's no critters in there. Why is this great for geologists? Obviously bad for biologists, right? It's dead. But for geologists, it's great because in the modern world, critters on the bottom of the ocean and lakes, they dig down into the sediment. They go 30 feet down into the sediment, and they mix it all up. Any layering that we had there when it was originally deposited, it's destroyed. Okay? Those little critters, they just massacre the layering in the rocks. It's horrible. Wonderful for biology, but it's horrible for geology. So if you want to study the layering of rocks back before last year, you've got to go to a place where there ain't no critters. Okay? And these hurricanes, bad for biology, great for geology, okay? If these hurricanes have taken many, many thousands of tons of sand off the beach and carried them out into the deep water and covered up entire communities of organisms. But 1 year from now, you'll go down there and you won't be able to tell. Those organisms will have recovered. They will have dug down 30 feet and mixed all of that material up, and you won't see any evidence of the hurricane. It'll be gone. 1 year, and it's gone. So if you want to study the sediments from the past, you got to go to a place where people have nuked the little critters, like Ducktown, Tennessee, or something like that, or you go to a place where there ain't no critters, like the Dead Sea. The Dead Sea, we've got these beautiful sediments. Mud has been dropping down into the Dead Sea for thousands of years, and critters haven't been messing it up. And so Steve's been going out there. He likes this. He loves this, the mud of the Dead Sea, because it's got a history going back thousands of years. And here, for example, is layers of mud. Look at this layer. What happened here? An earthquake. An earthquake went through that and convoluted the sediment after it was deposited. And we've been able to determine that this particular one, actually this whole set of layers here, was deformed in Herod's earthquake of 31 BC. That's cool. That's cool. Guess what? Not only that, but I mean, you know this of Steve's work, haven't you? I mean, how many are familiar? Most of you are familiar with this. And we go 60 years up, and you find the earthquake of the crucifixion. Okay, now notice the height here. This is only a few inches. This earthquake, which we estimate to be about a magnitude 7 earthquake, deformed the sediment about 1 inch to 2 inches, something like that. There it is there. Can barely see it at this scale. But here's another one. Look at this one. Big deformations there. 6 inches. 6 inches of deformation. That is the earthquake of 750 BC, which is the Great Uzziah earthquake. We estimate to be 16 times the power of the earthquake of 31 BC. 16 times the power. And it's about 2 times the height. Convolutions are about 2 times as high. So we think that that's the scale. If you double the height of the convolutions, you are increasing the magnitude of the earthquake about 16 times. Now note, that's 6 inches. That's not 6 inches. This is about 6 inches. I've got about 3 feet here. 3 feet. How big is that? That's kind of big, okay? In fact, a number of these 3-foot thick seismites have been identified around the world now. It's almost becoming a fad. There's probably a dozen of them been identified now. Every time a conventional geologist sees one of these things, he goes, whoa, this is big, okay? I mean, this is bigger by 16 times 16. What's 16 squared? Okay, 266 times bigger than the biggest earthquake we've experienced in 3,000 years. What? Really? But this is a baby. In my research, this puppy is a baby. This one that I traced over a half mile is a seismite. Right at the road, it's itty-bitty. It's only 6 feet thick. Walk along here, more and more of it gets exposed because of erosion from the creek. Over here, it's 30 feet thick. 30 feet of convolutions. That is tens to hundreds of thousands of times more powerful than the biggest earthquake we've experienced in the last 3,000 years. And if that was the only one here, that would be impressive, but it ain't. And I can trace those seismites over 13 miles of distance. It stands to reason. If an earthquake earthquake that big, it's going to be felt across the entire continent. You're going to see it across the entire continent, okay? So these puppies can be traced over long distances. Notice in these particular localities, I've got 5 of them. But remember, I've got a half-mile thick unit. I've got every 80 feet, I have one of these puppies. There are hundreds of them in this particular unit. So we have convoluted bedding, which means it's rapidly deposited sediments that are underwater, and they're fluidized by earthquakes. Scale is missing here. My notebook is sitting right over here. So this is about 6 feet. It's my size. This is about the life size right here on the scale. So it's one of the little ones. They're more than 3 feet thick, so they're much bigger than any modern earthquakes. Conventional geologists call them unearthly. They say there's no earthly process that can produce anything that's 3 feet or more. This is 6, and I've got 30. I've got 30 feet. Okay. They say the only way they know that this can be done is with an asteroid impact. Okay, so they would say this is an asteroid impact. But the problem is, I've got them every 80 feet, up 2,500 feet of sediment. I've got scores of these things. They can't be asteroids. You can't be hitting the Earth with asteroids that frequently. Nobody in the secular world will buy this as asteroids. So there must be some earthly process which produced earthquakes of this magnitude. Earthquakes that probably had a surface revelation. You would see waves in the ground coming towards you that were probably in excess of 30 feet in height. So nothing would survive. Nothing. You'd get kicked up when the first wave hits you into the air, you'd come back down, and all your bones would be smashed, and the next wave hits you. Every organism on the planet would be dead from these earthquakes. They're big, bigger fluid avulsion structures. This is astonishing stuff. And bigger. Oh, my word. This is awesome stuff. All I can say is, yikes. Ouch. I have at this point, this day, today, this week, one mechanism I can think of, the only one I can think of to explain this. In catastrophic plate tectonics, we've got plates moving at meters per second, diving underneath the continents. If on top of those plates that are going underneath the continents, there are islands attached, then when they go under the continent, they will smash that island up against the continent and accrete it onto the continent. Moving at meters per second, large islands should produce earthquakes of this magnitude. And they would send shock waves across the continent every time an island hit. So this would create these islands would get smashed onto the side of the continent and be a rock that doesn't fit any rock around it. And others would be accreted. You would looked at now, today, from above, we'd be walking along familiar with the geology and all of a sudden run into a rock that doesn't fit. And if we followed it, we'd find that it was all squashed and applied to the continent. We've called these things suspect terrains. Georgia is full of suspect terrains. California, Oregon, Washington, Alaska, that whole region wasn't there before the flood. That's all suspect terrains. Those were all islands that were smashed up against the continent by the subducting material. I think that's the only way to explain these earthquakes. And you can only do it with the catastrophism in creation model. This is one of those seismites. Just to remind you, this is a dinosaur bone sticking out of it. The dinosaurs are in the middle of this, okay? They're buried in the, remember, I'm studying the rocks that dinosaurs are found in. So if we want to know what killed the dinosaurs, that's it. The dinosaurs were wiped out by these incredible earthquakes, okay? So what do we got? We've got evidence for these things being underwater. It's the only way to explain the shell beds, the bones in the center of beds, the sheet sandstones. Sandstones, didn't mention sandstones with mud clasts in them, can only be done underwater. The convolutions I spoke of. The fact that it's deep water is indicated by the underwater mud flows. The crossbeds in the sandstone. It's fast-flowing water based upon the crossbeds. Even faster flowing based upon the conglomerate crossbeds. Sorry, it's misspelled. Rapid deposition. Skeletons of articulated skeletons, whole bodies, whole dinosaurs were deposited and preserved in that way. Concretions around bones. Almost all of the Triceratops skulls were found in concretions. Concretions are formed chemically by chemicals in the sediment after the fossils were deposited, being attracted to decaying organic matter. So concretions mean that was once flesh. So these dinosaur bones, even the isolated dinosaur bones, had flesh on them when they were deposited. Very rapid deposition. The convolutions, the closed bivalves, catastrophic plate motion at meters per second, which is, 3 billion times faster than current motions of plates. 3 billion times faster. This is the catastrophism of the flood. In addition, this is a post note that I put on this afternoon. I put into the talk this afternoon. We need to be reminded of the effects of moving water, because also at the same locality is not just evidence of the flood, but evidence of the world after the flood. And here we need to know that as the power of water increases, as you speed up water, it does more work. It can do more amazing things. At the very highest speeds, and it can actually erode flat. It can, normally you're familiar with water cutting gullies. That's when you got a small amount of water. When you have a lot of water, it actually cuts horizontally and shears things off flat. That's at the very, very highest velocity. And as the velocity decreases, the dip increases. So at the very highest velocity, it'll cut nearly horizontally. But as it slows down, it can only cut, it's going to lose energy as it goes downhill. It can only cut at steeper and steeper angles. And of course, at the highest velocity, it can go through solid rock. At lower velocities, it can only cut through softer sediments. As you slow it down, it can no longer erode, it can deposit. Everything that it's picked up while it was eroding, as it slows down, it can now dump it. And it dumps first the big stuff, the boulders, and then as it slows down further, it dumps the cobbles, and then it dumps the gravel, and then it dumps the sand, and then it dumps the silt, and then it dumps the shale. Okay, so a decreasing particle size is dropped out as it slows down. It also steepens its dip as it slows down. So when it's depositing at very high velocity, it deposits a flat bed. As it slows down, it deposits it, think of an avalanche, very steep slope. It's coming pretty slow. That's, relatively speaking, deposited slowly. Then, after sheet deposition, it will begin to channelize. It will begin to create small gullies, small relatively speaking. It'll start out with wide gullies, and it will decrease the width of the gullies as the speed decreases. It will start out with kind of U-shaped, not real bowl-shaped like glaciers, but sort of a square-shaped valley. And then as it slows down, it becomes a V-valley in time. These two sides will come closer together. Okay, so this is a way that you can roughly tell the relative strength movement of water when you're looking at features that you see on the surface. For example, go out west to Death Valley, spent a decade studying rocks in the Death Valley region, and here's a characteristic profile of the mountains around there. You've got mountain ranges, and you've got alluvial fans dropping off of the mountain ranges, and they're sitting on these very broad, inclined plains that lead up to the mountains. Many times the mountain ranges are so close together that the two from each side connect. But if they're far enough away from the next mountain range, you'll see that there's another angle that goes out from there. In cross-section, this is what you see, that there is a surface down here, which is called a peneplain. It's an erosional surface into solid rock that is very flat. Sitting on top of it is our sheet sediments. Sediments like sandstone, sheet sandstones, very thin, horizontally deposited units on top of the peneplain. Then on top of those are sloping sediments coming off the mountains called a pediment. Pediment, foot. It's a foot, a foothill in a sense. And then alluvial fans at a higher angle sitting on top of the pediments. And then there are channels in the alluvial fans. And then there are gullies inside the channels. And in places like Death Valley, there's no water at all inside those channels. Now, I say Death Valley because in places where it rains a lot, like around here, you think it doesn't, but it does, comparatively speaking, it's washed most of this stuff away, and so you can't find it. It's only in desert regions that are desert today, where you can see these evidences of things of the past. Here is the order of events. We first had an erosion. Water at very high velocity is eroding a horizontal or near horizontal surface. As the water slows down, it deposits sediments in sheet form. As it slows down further, it erodes them, it deposits them in sheets, but at an angle. And as it slows down, it increases its angle even more. And as it slows down, it produces channels in those. And as it slows down to the present you have what are called underfit rivers or creeks, tiny little creeks in bigger channels that those little creeks didn't make. The oldest, the first one, is, I believe, formed as the waters are receding from the continents. And the most recent of them are the modern channels. So this is a story from the end of the flood to the present. It's a story of decreasing water velocity and power. Basically, I like to put it this way. Here's a profound statement. I think the wettest period in Earth history was the flood. And then the Earth dried out since the flood. The biggest catastrophe in Earth history is the flood. There were residual catastrophes following the flood. They've reduced down to the tiny little residual catastrophes we have today, like Hurricane Emma and things like that. Little tiny, itsy-bitsy, teeny-weeny little catastrophes in the present. And the story of the flood to the present is a decreasing catastrophism as we go to the present. We see the same thing in the Grand Canyon. In the Grand Canyon, we have a canyon. We have the Kaibab upwarp, sort of like a dam that was produced to back up water in this direction. The Grand Staircase to the north of the Grand Canyon. If you blow up the bottom of the canyon here, you find that there's a little tiny river, the Colorado River, in the midst of a much larger canyon. Very often, it's very much smaller than the whole canyon, and it's not running on solid rock. The solid rock is somewhere down below. There is a bunch of sediment. It is not cutting the Colorado River, even before the dams, is not cutting into rock. It hasn't cut into rock for its entire existence. It is only cutting into sediment. And the sediment was from an event long before the formation of the Colorado River. So the events, we have a peneplain, which is the receding waters, I believe, of the flood, that it cut this plateau into that shape. There was no canyon here. Then later, we have channel erosion into that. This is after the flood. Then we have colluvium, what we call colluvium. It's just junk, just debris, sand, mud, that sort of thing that's left in the bottom of the channel. While it's running fast with water, it's cutting into rock. As it slows down, it dumps most of its load and fills most of the channel. I don't know how deep this is. This could be very deep, likely to be very deep. Then you have an underfit river. A river is just too small for this enormous canyon that it's in. So the events in order are here. The peneplanation, the erosion here, I believe, is at the end of the flood. Then after the flood, you have pretty big erosional event that produces the canyon. And as waters slow down from that erosional event, it drops out the colluvium. And then in the present, you have this tiny little river known as the Colorado River. Once again, the story is as it was in Death Valley, decreasing power and quantity of power of water in the as we go from the flood to the present. Now the story, we're back to Lance Creek. Let's look at the big picture. Rockies to the Appalachians with the Mississippi River in between. There's a long, slow drop to the Mississippi River. You can roll that rock all the way in both directions. The lowest point is the Mississippi River. This is cut into rock. This is a peneplain, a huge peneplain. It's hundreds of miles across, thousands. It's in excess of 1,000 miles across. This is a big peneplanation event, okay? And my focus is going to be on a little bump that's right here that you can't see. Let's look at that. Here's a little bump. It's known as the Black Hills, okay? And then my stuff is right here on these little bumps over here. This is Lance Creek over here. At this scale then, on top of this big peneplain, we have a pediment, we have sheet sediments coming off of the Black Hills. And they come all the way over to Lance Creek. And I find them on the tops of all the highest hills in Lance Creek. Rocks that do not come from any place except the Black Hills. And in between, there's these big valleys. So it was at a time when there was sediment sloughing off the Black Hills all the way to Lance Creek, some 50, 60 to 80 miles away. So there's a peneplain underneath, and then there's boulders. And these are up to 2 feet in diameter, boulders coming off of the Black Hills, 60 miles away. 2-foot diameter boulders being carried that far by water. Pretty impressive. Now, blowing that up, on these flat areas, I find the boulders from the Black Hills. And then cut into them are these creeks. Lance Creek, Lightning Creek comes into Lance Creek. You can also include in this Cheyenne River is also another one of these cut into that surface. So they're due to channel erosion. The scale is dropping here. The peneplain is hundreds of miles across. The boulder deposition is only tens of miles across. The channel erosion is only tenths of miles across. And then inside there's colluvium. Lance Creek is not cutting through rock in the base. It's got a bunch of debris it's cutting through that was left from the original deposition, the channel erosion when it slowed down. And then now, sitting in the middle of these, are underfit streams, little itsy-bitsy little streams, going back and forth across these wide channels. So again, the order is given here. We first have an event that peneplains the entire North American continent. I believe the receding waters of the flood. Then we have, in the post-flood time, very high erosion of Black Hills and deposition of boulders up to tens of miles away from it. By the way, there's a boulder bed that goes all the way across here from the Rockies, an amazing boulder bed in the Eocene, very earliest post-flood times, really big sheet erosion, sheet deposition. Then their channels come next, creating the Lance Creek, Cheyenne River, all those drainage systems. And then as it slows down, it drops colluvium in, and then the modern streams are most recent. So again, we got a story from the receding floodwaters to the present of decreasing water power and volume, just as we did before. So the whole story, we've got evidence of flood deposition in the Lance Formation, 2,500 feet thick, a half a mile of sediment over over thousands of square miles of area, hundreds of thousands of square miles of area, basically continental deposition. It's due to global scale catastrophism of the flood. We have the receding flood erosion, which is across continents, not globally, but across continents. And then we have post-flood erosion and deposition, which starts out regional and gets smaller and smaller to the present. So we had a story of the late flood and post-flood times in the Lance Formation. And thanks to all those ranchers that let me walk across their property without shooting me. There's a couple not on here. There's one that thought I was an axe murderer, so I still haven't gotten permission to get onto their property. I don't know how to not be an axe murderer. When I showed up in their church, she came up to me and said, "Well, I guess you're not an axe murderer." I said, "Well, I mean, this would be a great place to hide out if I was an axe murderer, wouldn't it?" So she didn't let me on her property. I guess you don't joke around sometimes, right? So thank you. Well, that was a lot. About half of this isn't published, so it should be published next year in the Creation Geology Society meeting. Yes? I gave a talk at the Geological Society of America meeting arguing for the underwater deposition of the Lance Formation. That was fun. They were okay with my argument except for one thing. They asked a really important question, which was, what about the fossils? Do you find any marine fossils? Nope, no marine fossils. Well, then how can you explain this? If it's got no marine fossils, how can it be a marine deposition? So that's a very good question. Looks like it's a bunch of organisms from the land that were overcome by a marine transgression, very rapid marine transgression. So they're actually freshwater clams. Mm-hmm. Yeah, all of the clams, all of the fauna. Now, there's some things that could be saltwater, but actually all of the organisms could be, all these aquatic organisms can be freshwater. There's gar, there's alligator, turtle, but all these things can be terrestrial. So there's only one, and I've been digging up all the literature on at least the type locality, and there's only one report I've seen so far of a marine fossil. It's 80 feet up from the base, so it could have been, could have been moved up and redeposited in there, and it's a marine shell, and that's it. Otherwise, thousands and thousands and thousands of fossils, and all of them are terrestrial. Which is another interesting thing about the flood. It's one thing I've got to actually publish because I'm aggravated with creationists who keep lying about this. You do not find marine and terrestrial organisms mixed together. It's almost unheard of. There's a few places where it happens, but somehow the flood was able to keep those two things separate, even though it would deposit marine sediments for miles of marine sediments and then miles of terrestrial sediments, and once again marine sediments. It almost never mixed them up. So that's an interesting thing about the flood. It's something very interesting about the flood. It requires some very special explanations, which we don't have at this particular point. No, that's quite the opposite. When we find deposits across entire continents, let's say there's some Ordovician layers that are found across all of North America, and they're marine. But all of North America, all of it that has any rocks. Now, there's some places up in Canada that don't have any flood sediments at all. Okay, but aside from that, in any place that has flood sediments across the entire continent, we have marine sediments. Thousands of feet higher, we have these sediments, which are all terrestrial. So in order to do this, you would have to keep the terrestrial organisms in the water column while you're depositing marine organisms underneath them. You've got to pick them off the continent, keep them together, because they seem to be kept together in ecosystems. The flood is picking up entire ecosystems, carrying them, I believe, around the world multiple times, and then dumping them. Meanwhile, in the layers underneath it, they're dumping other ecosystems. So it requires it requires laminar flow, which is a weird concept. In the modern world, almost all water flows in a turbulent fashion. It carries things and rolls things along the bottom. It doesn't carry things at one place in the water and keep them at that one level and just keep going with it. It usually drops it and rolls it. This would require laminar flow, where the flood is actually keeping entire ecosystems. Probably hundreds of feet of water are being kept at one level and basically circulating around the world while things are depositing underneath it, while erosion is occurring underneath it, and these things are being kept wet and together. Fascinating, really fascinating. So, someone, oh, okay, you want to, I don't know if is that thing working? Yeah, guess it is.
With the laminar flow, it would seem that your higher density organisms would separate out pretty quickly from
Now, in in laminar flow, things do not separate out. In laminar flow, they remain mixed. In turbulent flow, the heavier things fall out.
Do these deposits have fragile and durable fossils together?
Mm-hmm.
If you have that kind of laminar flow going around the Earth, how do you keep the fragile fossils from totally becoming unrecognizable?
Because it's laminar flow. If it's turbulent flow, things are moving and there's relative velocity within the unit, so small things hit big things. In laminar flow, it's moving together. Nothing's moving with respect to anything else. So if it's separated, this happens, for example, in a type of avalanche known as a stirstrom. It's fascinating type of avalanche. As you increase the size of an avalanche from small avalanches, it basically just increases their size. Everything stays the same. It's about twice as wide at the base as it is long. And as you increase the amount of debris, it just gets bigger and bigger. But at a certain point, it hits a threshold value. When you exceed 1 billion metric tons of material, and you drop it in excess of 1 kilometer, when it hits, it takes on completely different characteristics and becomes what's called a stirstrom. That rock unit will move as a unit, laminar flow, moves across the landscape at about 220 miles an hour, and ends up, when it stops, sort of freezes finally, when it goes right through towns, just obliterates town. It's a wall of rock. It's what's called Sturstrom, river of rock in German. It goes right through towns and then freezes in place 12 times longer than it is wide. Completely different. And the fact that it's laminar flow can be evidenced by the fact that boulders that are in it, when it hits, explode. And then they move as a unit all the way to the end. We found boulders, we know where they come from, and they're found 12 miles away, exploded. All the pieces are separated a few inches from each other, but in the same relative position. So once they explode, they never move with respect to one another, all the way to the end. It's really cool. It's called jigsaw puzzle texture. When you cut through it, it looks like a jigsaw puzzle, and you can put all the pieces back together. It's wild. It's interesting because this is one of many what we call threshold processes in geology. We study the process at a certain scale, and we see the pattern. It's okay, no problems. And then we hit this threshold, and now it's a completely different set of rules. And it's fascinating. These stirstrums, by the way, it doesn't matter whether it's water, air, or vacuum. We've seen stirstrums on Mars. We've seen they're underwater. It doesn't matter what the medium is. They go through whatever medium it is and behave the same way. So this gives me an encouragement, by the way, because the flood is really big. And all of our studies are on really small things. It's very possible that when we hit a certain threshold, certain size, that water's going to do something different than we're familiar with it. So I think laminar flow becomes, in a normal avalanche, it's turbulent flow. But in a stirstrom, it's laminar flow. And the possibility exists, I think, it's got to be, from what I see, that at the scale of the flood, water turns from a turbulent flow regime, which we're used to a laminar flow regime. Which, by the way, could solve another problem that we have in creationism, one that John Baumgartner has been wrestling with for years, has been producing all sorts of papers that I think are bunk because he's trying to solve it in the wrong way. But the curious fact of all these rocks are on the continents. They're not in the ocean. There are no flood sediments in the ocean. Almost no flood sediments in the ocean. They're all recent sediments in the ocean, post-flood. Why are there no flood sediments in the ocean? It's a very good question. I'm glad you asked. So here's the physics issue. Here's the issue that physics has to deal with. Let's say you have a creek that's flowing over an uneven surface. It's flowing at the same rate all the way down. Same amount of water is passing every unit, every point in time. But if it's a shallower section of the creek, because it's shallower and the same amount has to go through per unit time, it's got to go through faster. So rapids. Rapids are shallow areas. The water moves faster in rapids than it does in the deep part. You know, you're sitting there in that inflatable on those slow parts of the creek, you know, it just kind of moves around like that. I'm already dizzy. I can't do that circular stuff. And then you get to that rapids. Okay? And I mean, it's simple physics. The same volume of water passing a unit, passing a thinner place has got to move faster. Remember what I said about faster water? Faster water erodes, slower water deposits. So if you're moving water over the surface of the earth and it goes over a continent, it's got to move faster over the continent. It can't be depositing over continents. It's got to be eroding the continents off and dumping them in the ocean. And so John Baumgartner's been struggling with this for years. He says, why in the world are all the sediments on the continents? They should be in the oceans. In fact, people have been struggling with this for millennia. For hundreds of years, people have argued that maybe the oceans were once the pre-flood continents, and they just dumped everything off onto the continents. It's not a bad idea until we learn about the bottom of the oceans, and no, that won't work. But here, if we've got laminar flow, if you're sitting at a certain position and you're going around the world at that particular level, you'll only speed up over the continents. You will not encounter turbulent flow. You will stay. Basically, the water between the continents is not moving. And the other is hydroplaning over the top of it. And so it can actually move, theoretically it can move faster, but it won't because it's moving as a unit. So it can move around the world at the constant velocity if it's laminar flow. And the only time it would stop is if it hits an obstruction and slows down, dumps, and it's not going to hit an obstruction in the middle of the ocean. It's going to hit an obstruction on the continent. So that's why I suspect it all. So laminar flow, I think, is going to be the hero of the story, if we can figure it out in the end. Sorry, go ahead.
If your water is fed up that much, going across the top of the
So let me get some water.
how do you get the marine deposits at the bottom?
Thank you. And the first system we have on the continents is erosion. You know, the first thing on the North American continent is the Great Unconformity. The Great Unconformity across the entire continent shaves off the entire continent some, I don't know how much. How do we know? Maybe thousands of feet. I suspect the pre-flood world continents were shaved off by thousands of feet. And that's the first event of the flood. The highest energy of the flood was all erosional, no deposition. It's only when the flood slows down, when it lowers its energy, that we begin dropping things out. And the idea there is that as the waters came up, the land creatures were buried. They're subsumed in a higher laminar flow than the marine creatures, which were inserted below them. So the marine creatures are actually circling the globe at a lower level than the terrestrial organisms. Although there's a mixture because we have some marine layers in the middle of terrestrial layers. I don't understand that laminar. It's got to be true, but I don't understand how it works at this point. Well, it seems the Grand Canyon is an example of that. And what would happen in that situation, I'd expect what would happen in that situation is that you'd destroy all evidence, because in breaching that dam, you're undergoing turbulent flow. I think you're just going to massacre all the critters and everything in that, going through that gap. If there was anything in the water, it's going to be destroyed. The evidence in the Grand Canyon confirms that. The downstream sediments of the Grand Canyon are in the Salton Sea. And the cyclical sediments of the Salton Sea, there's basically no fossils in there, with the exception of critters that grew in there afterwards. So that's not, and it's only going to be superficial sediments. It's only going to be those, it's not going to be the flood sediments. Right. But I don't know any examples of terrestrial sediments with terrestrial organisms that are downstream from a breached dam. Offhand, I don't know of any. So none of the bone beds in the Cenozoic, as far as I know, are that way. Bone beds, we got ashfall bone beds. We've got bone beds from in the middle of sheet deposition it's a long ways away from any potential dam areas. We've got stuff near the ocean that is coming in from the ocean. I don't know of any from breached dams. Interesting question, but I don't know of any. Right. Yeah, really small. Yes, we do. I mean, again, what I start with is data, well, actual rocks. This is what I have problems with John Baumgartner and others. These models are great, but typical of physicists, they don't really care about the data. They can create beautiful theories that actually dump all the sediment on the continents, but his most recent theory he gave this last summer, I guess it wasn't that too long ago, a couple of months ago, And the problem is that his theory predicts that the thinnest sediments will be on the edges of the continents, and then the thickest sediments will be in the middle. And that's the opposite of what you actually see on the continents. So that won't work. He also predicts that there should be circulation in a circular fashion on the continent. And we've got paleocurrents that indicate that they go across continents. So we can eliminate that. I mean, it's a beautiful theory, but it just didn't happen in the past. And some of the things you're talking about also didn't happen because Art Chadwick's paleocurrent data is extremely important here. When we see across continents, and basically all the continents, a pretty much uniform direction of currents in one direction, we're not talking about back and forth flow. There's no back and forth flow occurring of any significant at least during deposition in the flood. So that helps us. That's a huge help to us. Then we have some sort of a standard to start from. Also, the amount of sediment where it's at. The fact that the sediment is deepest on the edge of the continents and shallowest in the middle is also very interesting. That, among other things, confirms the fact that the continents actually existed, and that they are resistant structures that you can deposit on the edges of more than in the middle. That's very important information. We would predict that from our understanding of the geophysics, because plate tectonics won't work unless we actually have oceans and continents. And there's evidence that there were oceans and that plate tectonics really did occur in an accelerated fashion. So we have some reason to believe that the modern continents existed in the pre-flood world. That isn't to say there might not have been other continents. But the continents that we now have were continents in the pre-flood world. Not necessarily in the same arrangement they are now, but they were there. That's helpful information as well. When you start putting all these pieces of information together, we can eliminate some of the ideas that people have proposed. But you're talking about tidal. Something that's been suggested more than once in creationism is the idea of tide, where the moon actually holds the water and the earth spins underneath it. So we're not talking about tides in the traditional sense of the word. The moon holds the water, the earth spins around it, the waters drop out because the continent goes underneath the moon. But if there's no continent that goes underneath the moon, and you got a worldwide ocean, the moon can potentially hold the water in place and the earth spin underneath it. At the equator, that would move the land 1,000 miles an hour underneath the water. And at our latitude, about 700 miles an hour, which may, in fact, induce that laminar flow that we're talking about. It would mean shallow oceans or shallow ocean over the poles, much deeper over the equator, and maybe some amount of that is going on. Because that would create a uniform east to west current direction, which is what we get from the paleocurrent data. Paleocurrent indicates that all the sediments are being deposited by the major direction of motion of water is from the east to the west. And that's exactly what would happen if, in fact, the Earth was spinning underneath the water held up by the moon. That's interesting. Something to consider. Not something to ignore. It's something to actually consider. The problem here comes, you can't look at the present orientation of the continents. It's the orientation of the continents at the time of deposition. And when you reconstruct that, it is very close to an east-west. Now, that needs to be redone because we're using the continental configurations produced by secular scientists. And they're really good with the information that they have. But some of the data they're using are data that we would interpret differently. For example, the Permian glacial deposits, the Permian diamictites, are interpreted as glacial. And I think in creationism we would not. They are underwater avalanche deposits, as are the upper Proterozoic diamictites. That I argued that with Steve Austin back in '94 or something like that. Those, what is generally described as the frozen Earth. What's it? I forget the term. Snowball Earth is from diamictites that are found at the equator at that time. That, if they're deposited by glaciers, means the whole world has to be covered by ice. But those particular deposits in Death Valley, Steve and I have interpreted as underwater avalanche deposits. So that's an example of the kind of data that they would have said, oh, well, that means it's high latitude. We have to reinterpret all of that to create correct maps of the orientations of the continents during the flood. But my suspicion is that when we do that, we're going to have things being extremely close to east-west almost throughout. Now, right now, during a certain portion of the geologic column in North America, they are coming from the northwest and going to the south, northeast to the southwest. But when you look at the paleomag, the continent is rotated. So it's actually east to west. Still work to be done. We need lots of help. Lots of work needs to be done on that sort of thing. I haven't turned my attention to that yet. Yes. Excellent question. I'm going to answer it in two ways. One, I'm going to give you one example from a completely different level. And two, I'm going to argue that there's probably a lot more out there than anyone has acknowledged. Number one, one of the people I worked with at Bryan College got his doctorate at the University of Kentucky and did his dissertation work on some Ordovician limestones. They're actually breccias. The limestone's been broken up into pieces. It's been brecciated. His advisor put him on this project as part of a whole bunch of projects that he put a bunch of students on across the continent. And he was looking for places where the limestone, while it was relatively new, having recently been formed, that it gets brecciated somehow. Limestone was originally a mud, a very gooey, limey mud, but it sets really fast, relatively speaking, and becomes brittle very fast. So in some cases within a day, but certainly within weeks, even in modern situations, it becomes brittle faster than just about any other type of rock. These brecciated things are, the rocks above and below are not brecciated. They're not broken up, but they're also not limestone. So it suggests that something came through the rocks and deformed the sediments, but the other rocks were still soft, so they could take it. But the limestone was brittle and broke up. So he's arguing, his advisor was arguing that these are actually seismites. This is another evidence of a big earthquake that went through the rocks. But in this case, it's able to break rocks in the middle of the unit. rather than deform the soft ones, it's actually breaking the brittle ones. What's that? That was in Ordovician. But the other graduate students were working on the same kind of rock at different levels in the geologic column, all the way from, he traced the oldest ones in the eastern U.S., and he gets and younger as we go across the continent. So this is, I'm telling you the gospel truth here. This is what I'm about to say should blow your mind. No way can anyone believe this. But this is what the guy said. This is all from one event. An event that caused a deformation of the crust of the continent, that as it moved across the continent, it broke limestone beds that are only about a foot thick, shattered them. As it moves across the continent, it shatters limestone beds all the way across the continent, and it takes 100 million years to cross the continent. If if I didn't actually see the work, if I didn't hear it from the guy himself, if I didn't hear it from his graduate students, I wouldn't believe that anyone could think of such a thing as this. This makes no sense. There's nothing we know of in physics, material science, anything that can cause a deformation that could shatter rock, move across the continent in 100 million years. Things move at the speed of sound. That means 100 million years of deposition occurred in hours. But I think it's another type of evidence of the kind of earthquakes we're talking about, okay? So that's my first response. I think there is evidence for more of these. Secondly, I showed you that picture. I said, this is a road that's on the 1897 map. It's the major road used by geologists for over 100 years. If you take that road across the creek, I'm sorry, I didn't do it, across the creek and up through that sandstone unit you could see, if you drove a little too close to the side of the road, your mirror would be knocked off by one of these seismites. Okay, it's right there on the side of the road. You don't have to get out of the car to actually look at it at inches away. And it's a little guy at that point. It's only 6 feet. It's a 6-foot convolution right there on the side of the road, and you can see it go for half a mile in that direction, okay? Getting bigger and bigger and bigger. John Bell Hatcher, 100 years ago, saw that. So did every single geologist that has been in that area ever since collecting dinosaur bones. And as I said before, you may not have caught it, it's never been published. No one's ever mentioned the fact that the convoluted bedding is there. Everybody has seen it. And I have looked through the literature. Again, I'm not quite done yet. I have something like 1,600 references. But I'm not quite done with all the literature that's been published on this unit. But so far, I've found only one reference to it. It's a 2002 publication in a figure caption. Not anywhere in the article, but in the figure caption, it's got a picture of convoluted bedding. And it says, here is the typical convoluted bedding of the Lance Formation. That's the only place. I've even got I talked about a guy that tried to make a type section. He did very careful study of several locations to several sections, and he's published them. There's descriptions. He describes, here's this rock. It is 3 feet thick, and it's got this in it. It's got these sedimentary structures, and it's got this color. And then there's 6 inches of this, and then there's 12 inches of this, and then there's 4 feet of this. All the way up, I've gone to those 3 localities, and I've looked at the same rocks. I've created my own stratigraphic section. I can compare them one by one. He did a good job. Every time he came to a convoluted bedding, he does not describe it as convoluted bedding. It's cross bedding. It's not cross bedding, folks. It's convoluted bedding. It's right there. He looked at it. He studied it as a graduate student, and he still didn't see it. Geologists have been looking at that for over 100 years, and they've never seen it. If that's been the case there, could it be somewhere else? Yeah, I suspect it's all over the place. It's just not been observed because, I think in part because, I have no idea how that's formed. Or, I have an idea how that's formed, and it can't be, so I'm going to ignore it. I don't know what the reason is, but I suspect it's everywhere. It's been, as I said, there's about a dozen instances around the world that I've found in other locations. One place even argued that it was every 60 feet on a regular cyclical basis. So we've got these earthquakes coming at regular intervals. That's pretty cool. And I think I can argue for the same thing here, that it is very close to periodic. It's almost consistent. But that's according to burial depth. So we're dealing with things that don't get buried at the same rates. Sandstone and shale and sand don't get buried at the same rate. But anyway, yeah, I suspect there's a lot more. Great question. Hey, take up the banner. You could do this all around the world, be the world's expert on it. And there's one up there at the KT boundary, the one with the iridium layer. There's one of these huge ones, 25 feet thick, that's sitting about 30 feet below that boundary. There's another one that's sitting about 30 feet above it. I thought at one point, this would be dishonest, but it's very tempting, is to publish a paper on the one that's closest to that boundary and say, I found the evidence of the asteroid impact. And I get famous. I wait a little while, and then I go, oh, and there's another one, and another one. Oh, I guess that wasn't the one after all. But it would bring people's attention to this locality. Might be the only way to do it really well. You want to get in real big trouble? You can try that. Be my graduate student. Yeah. Are you asking what the standard is in the field typically? What happens in the field? Yeah, if I submitted a paper, like even the Geological Society of America paper that I submitted, that I said I argued for the underwater deposition here, that was peer reviewed. So I send it to an editor. That editor has a number of experts that he or she is familiar with, and he'll take that paper, cut out the person's name, send the paper to generally 3 of the experts they think are most qualified to deal with this, and that would almost, if it's a paper that's critiquing someone else's work, they'll almost certainly send it to that person. Among all of those that it's sent to. That's standard procedure, which, by the way, is not in creationism. This is something we got to stop. We got to start doing things right. We're not reviewing papers properly. All sorts of things. Generally, 2 or 3 papers are published every year that critique my work. I never see them, and the author should send me a copy before they publish. That's the standard. If I was publishing something against some person in England, I would send them a copy of the paper before I even send it off for publication. And then the publisher will likely send them a copy to review it. Then what happens is the editor will collect the responses of the reviewers. The editor will and the reviewers are asked to, number one, recommend to the editor whether it should be published at all. There's really 3 options. Publish it just as it is. It's spectacular. It's magnificent. That never happens. Number 2, this is such trash you shouldn't even consider, and I'm not going to tell you anything more about it because there ain't anything worthwhile in it. Okay, that usually doesn't happen either. The third option is publish it, but only after these kind of changes have been made, and if these kind of changes are made. So then the editor will take all that advice, and the editor will make a decision. It's the editor's choice as to whether they might get 3 rejections and still say, I think it's worth publishing anyway. But usually what happens at that point, the editor will recommunicate with the author, send it back to him and say, here's the changes I want you to make. If you make these changes, I'll publish it. Or, sorry, we can't publish it. And sometimes with the sorry will be the reasons given. Sometimes the editor will give you all of the criticisms of all of the people involved. Sometimes only excerpts or snippets. It's the editor's choice as to what. And it is the editor's choice because usually the editor is paid by the journal, and if they don't do a good job, the journal fires them. So they want to do a good job. So does that answer your question? Yeah, and some editors really like that. So they like to put things in that are controversial, and they try to do a good job of making sure the argument or the discussion is kept at a high level and not ad hominem back and forth, but we're actually arguing on the basis of data and evidence. And it is double, I didn't say that, but it is double blind. In other words, when the editor communicates back with the author, the reviewers aren't revealed. Sometimes both parties can figure it out. The reviewer can figure out who wrote the paper, and the author can figure out who reviewed it. That sometimes happens because the field is kind of narrow. How many people are experts in fluid emulsion structures, for example? I mean, you usually know them, but it's otherwise double blind. After the half hour? Yes.
So you're only going to see it if the earthquake happens to come through in a layer that's at the top of the stack.
Very good, right?
So just wanted to
Excellent point, yes.
Okay, so let's see. Next comment I wanted to make is in regard to I guess it was the laminar flow issue and holding the oceanic fossils, the different layers, and the terrestrial fossils. I was just kind of brainstorming about that when you mentioned it, that I wonder if there could be a sort of a loose analogy to air masses, because air mass in meteorology, depending on the temperature and the humidity of air mass, doesn't tend to mix with another air
Right.
mass that's a different
Yes.
humidity.
Quite true.
I mean, probably the dynamic of that is quite different, but maybe it isn't.
Same fluid dynamics.
Ocean currents, the temperature of ocean water will cause one current to remain within itself, and
Yes.
and it won't mix with the other water around it. Final comment I had is
Remember these?
this one is
Mm-hmm.
And you mentioned that the speed of the Earth is 1,000 miles an hour at the equator. But and maybe you can elaborate on this, but I'm kind of having a little difficulty understanding how that might happen because the primary effect of the tide is not to pull the water horizontally, but is to pull it vertically away from the
Mm-hmm.
away from the surface of the Earth. So it would seem to me that as the Earth rotates under the moon's pull, that it wouldn't be dragging the water along with it. It would be more like a big standing wave. And wave action, I mean, typically the particles in the water will go around a little circle in a typical way. In a gigantic wave like that, it seems like they might just go up and down instead of horizontal. And
Mm-hmm.
that might be my question is there something more to the dynamic that I'm not understanding?
Okay, very good. Now I'll see if I can remember these. First of all, yeah, the geomorphology stuff, the broad erosion of the peneplain and that sort of thing, I added that this afternoon. That was today's theory. I'm going to publish that next year. Yeah, that was pulling together several things from my research in Death Valley, my research in Lance Formation. I had one slide before that. Previous to that, I had one slide talking about miscellaneous things I've observed in Death Valley, and I've always wanted to expand upon it. So I think it's pretty cool, too, but I'm a little biased. And by the way, I don't want to be too mean about this, but Mike Ord has a completely different view of things, and he's got what you said. Geologists have this problem traditionally of thinking too small, and that's really because of how we're trained. We're trained in looking at road cuts, things that are about 20 feet long, a foot high. That's what we're used to doing. Geophysicists sometimes look at logs that are geophysical logs that are hundreds of miles, but we don't usually get that opportunity when we're studying rocks. So we're trained very locally in our formal training. We're trained to think locally and think on local, usually not even regional scale events. So it's been very difficult for me to scale things up in my thinking over the years, trying to think bigger. I can remember when Steve Austin and I first went out to Death Valley, and we were mapping away on these layers. We spent a day or two figuring out what the layers were out there in the rocks we were looking at. We were all excited about that. We could see it, and we started to map. We mapped for an entire day. At the end of the day, we're looking at our maps going, this doesn't make any sense. We had put in it was, and it's just humorous now thinking about it. We look at our maps. We're sitting there in the casino because you get cheaper rates in the casino, and we're sitting in the casino and pushing apart the smoke from the cigarettes, looking at our maps, and we got these faults we'd put in, and we hadn't finished the project. We just had pieces of the faults. But if we projected them, we had circular faults that went in circles. It's like, what? That's stupid. That can't be. And we're thinking back over the day and said, no, that was a fault. I know that was a fault. The rocks came in at this angle, and on the other side of it, they were at this angle. That's a fault. That was a fault. I remember that. It was 11 o'clock. We ate there. We ate lunch there. I know that was a fault. And this was a fault. And Steve, he sits back as Steve typically does. He didn't say anything. I'm the one that's talking. I'm going, this is crazy. This is stupid. We're idiots. This can't, what's wrong? Steve didn't say anything. Finally, he says, maybe it's a boulder. What? What do you mean it's a boulder? What's it? What's your antecedent, doggone it? You guys in the military intelligence, you just don't have antecedents. Is it Russia you're talking about? And he says, well, maybe this isn't bedrock. Maybe this is a boulder. And this circular fault is the edge of the boulder. We've been mapping a boulder. It's a 1/4-mile diameter boulder. It's big enough to have layers of rock in it that we were in. It's a mountain. It's a whole mountain. And it's the edge of the mountain that was the edge of the boulder, which is the edge of the mountain. And I went, oh, that hurts. That hurts the brain. We had to go out the next day, and we had to walk back over that. Went, it's a boulder. Oh, my word. Now you have to rethink everything. Then we saw boulders. That was the little one. 1 mile, 2 miles. Amazing. Okay. We weren't taught to think that way, okay? The flood requires thinking way outside of the traditional way of thinking. And although Mike Ord is not trained in geology, he's also got, in my opinion, a very localized view. He refuses to accept regional correlation across continents, and there is regional correlation across continents. And he's thinking too small. You got to think on the level. So he's looking at things that I'm calling post-flood as being flood events. I'm saying they're too small. We've got to look at bigger things. The flood is global. Okay, but that's hard, I admit. That's really hard to think about. Now I really did forget what the second one. The seismites, give me one more. On the surface, yes. Yes, the seismites, and that's a very good point. It's an excellent point. It's only when sediments are soft, still full of water, that they can get deformed like that. If they're buried too deeply, they can't get deformed, which makes 30-foot thick units really amazing to explain, because you've got to deform 30 feet. That's a lot of weight that you've got to redistribute. But even then, the 30 feet's got to be on top of the sediment. Not on top of the water, but it can't be buried underneath other sediment. Now, I do have evidence of underneath the 30 feet that the shale underneath, the mud underneath, got shot through the sandstone. It's really cool. It gets shot through with layers. They're called clastic dikes. They shoot through the sandstone and arc over the top of the sandstone with big pieces of shale. So I know the stuff underneath the sandstone is also getting deformed. But it's shale, it's mud, and it doesn't deform in the same way. It doesn't do that same kind of convolution, and you can't see it, unfortunately, because these mud rocks don't get preserved, lithified. They don't get lithified. It's the other thing, I can't see sandstone that isn't lithified. I can't see convolutions in sandstone and 40 to 60% of the sandstone is not lithified at this locality. So I'm not getting all of them. But yes, the only seismites that would be preserved are those that are in surface sediments at the time the earthquake went through. So that's not all the earthquakes of the flood. They're only going to preserve some of the earthquakes. Yes, and you talked about an analogy with, I'm trying to do that, the analogy with air and water. Absolutely the same thing.